Yeah, thanks very much for the opportunity, and also the opportunity to have some conversation with the other program as well. So if I understand my mission correctly, it's to give a somewhat representative talk about what we've been talking about in the What is Particle Theory conference at a colloquial level. And now the problem is that what is particle theory is not really about one thing. So it's a bit of an interesting conference in that the attempt is to bring together all sorts of people who work on incredibly diverse components of particle theory. So in the last few decades, the field of particle theory has somewhat exploded and has ties now to astrophysics, to cosmology, to string theory, to low-energy condensed physics. And it would be very foolish of me to attempt to try and give a representative view of all of the topics that we've heard so far, which include things like the nature of dark matter, lattice QCD, the formal mathematical structure behind scattering amplitudes. So what I want to do today is sort of pick one thing and kind of tease out what I think is one common thread in a lot of the talks that we've heard so far in the conference. And that is the question of what can consistency conditions tell us about our theories of particle physics in the absence of data. All right, and I should say also, the joy of giving an overview talk is that probably for everything I say, there's a high probability that there's somebody in the program who's more of an expert about this than I am, and so I definitely encourage other people to chime in as well. But just to give a little bit of background, so what's known as S-matrix theory grew to prominence in probably the late 1950s. And this was related to the realization that when you try and connect quantum mechanics with special relativity, what you find is a certain amount of rigidity in your theory. So you come across this notion that in fact not anything goes and that your theories are remarkably constrained. And so there was this hope that you might be able to solve relativistic quantum field theories based largely on self-consistency and maybe some additional data as well. And now it turns out that that was really too optimistic. What we know today is that in general, quantum field theories aren't unique. You can have large swaths of allowed quantum field theories. This was a program that was much more readily realized by conformal field theory, where there you have more symmetries that can further constrain your theories. So in quantum field theory, it wasn't really able to be totally realized. And in that, I should say another one of the obstacles as well is that we still don't really appreciate or understand what the full set of fundamental principles are that we should be using in order to constrain these theories. However, what we can do is we can constrain the space of consistent field theories. And what that means is that we can answer questions like, does my IR theory admit a consistent UV completion? Can I bound coefficients on my low energy effective theory? And what can I learn about the spectrum of states in my theory? So these are all questions that are accessible given a certain set of consistency assumptions on your theory. And I'll talk more about these. So the constraint that I'm going to focus on today in trying to answer some of these questions is a causality constraint. All right, and causality appears in many different forms, and in fact, there are many different types of constraints that all go under the name of a causality constraint. All right, so in quantum field theory, what we mean by causality is really the notion of microcausality, which is the statement that if I have two operators that are separated, that have space-like separation, they should commute with each other. So this is for x1 and x2, space-like separated. And this notion of microcausality, in fact, you can think of as being a consequence of Lorentz invariance, and in particular a consequence of the Lorentz invariance of time ordering. So you can imagine that if you want to time order two operators, say this same O1 and O2, at space-like separated points, I can do a Lorentz boost to change the time ordering of these two guys here. So unless these two operators commute with each other, I wouldn't be able to define time ordering in a Lorentz invariant way. All right. Now, what we use quantum field theory for, usually at the end of the day, is to compute scattering amplitudes. And so you might ask, what is the manifestation of this microcausality in a scattering amplitude? In other words, if someone was to hand you some amplitude, how would you know that that the underlying theory that generated that amplitude actually obeyed this condition of microcausality? All right, so to get a better handle on this, we're going to look at a toy model, the signal model. Which you can think of as like a 0 plus 1D scattering problem. All right, so you have some initial signal, say psi in, as a function of t, some outgoing signal, psi out, also as a function of t. And these are related in the following way. So we can write psi out of t as equal to the integral over some t prime, s of t prime minus t, psi in of t prime, like so. Well, we can think of this s here as being our scattering matrix that encodes the interactions of this signal with, say, some background. All right. The statement then of causality is that if psi in of t prime is equal to 0 for all t prime less than 0, then it must be the case that psi out of t is equal to 0 for all t less than 0. In other words, you shouldn't get an out signal until you turn on your in signal. All right, and just by looking at this expression here, this tells you that means that s of t has to be equal to 0 for t less than 0.
Rachel, is it specifically local, like Lorentz invariance? Because we have other massively symmetric cases that have boosts as well, right? Just going back to your point about Lorentz boosting, preserving time ordering.
This here.
Yeah.
So I know this statement as a consequence of Lorentz invariance for quantum field theory. I think the statement is as long as you have theories that are locally Lorentz invariance, this is true more generally.
But you can break, say, Lorentz invariance by making, say, in time, let's use this kind of commutation, because about time order, but I can still differentiate the space movement in Lorentz group to be different, and it will be still okay with this. So I think it's locality is more stronger than does this.
Than this statement alone. Okay, I think that's right. Thank you.
One question just out of curiosity.
Yeah.
What do these violations of the Bell inequality, which has been observed, imply for causality and so on?
So violations of Bell inequality never let you sort of send information or impact something at space-like separated points. So it doesn't violate this in any way. You might worry about, so one thing you could worry about is cluster decomposition if you have states that are entangled, and that's a more subtle issue. But entanglement in and of itself, you can't impact if something is space-like separated, even if these things are entangled with each other. You can't make a measurement over here that then impacts the measurement over here, that changes the outcome over here.
But standard quantum mechanics predicted the Bell inequality, right? And now we see that they are violated. So on which assumption of standard quantum mechanics do you have to give up so that you can get this observed violation of the Bell inequalities?
So what do you mean in particular?
I mean, I talked to people from solid state physics, and they did all these experiments where the Bell inequalities, which are just derived from the normal Schrödinger equation, so just standard quantum mechanics, are violated. So you have to give up some assumptions which go into the derivation of quantum mechanics if you want to account for the violations of the Bell inequality.
Okay, yeah, I'm not an expert on violations of Bell inequality.
No, but this is, what you're saying is simply wrong.
Could be. I mean,
Let's not Rachel go ahead. Proceed.
Okay, very good.
No, I think it's too big.
Rachel's going to proceed, Arkani. Rachel's going to proceed.
Okay, very good. So just to make the simple point, if I write this 0 plus 1D S matrix in terms of its Fourier transform, so I have some frequency omega, e to the I omega, t of S omega, then what we want is the following. So this is telling us for t less than 0. This becomes S of t. I can write this as now the integral e to the plus I omega, absolute value of t, S omega. And this has to be equal to 0 for t less than 0. And so you can see right away that if this S omega grows slower than an exponential, and this is in the imaginary part of omega, goes to plus infinity limit, then I can calculate this integral by closing the contour in an upper half plane. So this is going to go to 0. And the statement that S of t then is equal to 0 is just the statement that this function S of omega should be analytic in the upper half plane. I shouldn't capture any poles or branch cuts or irregularities. So if S omega grows slower than exponential, I can conclude that S of omega must be analytic in the upper half. All right, so we get some notion that the way that causality is going to manifest itself in scattering amplitudes is in terms of the analyticity of the functions. Now again, these omegas, these energies are always going to be real variables, but what I'm doing is I'm assuming that I can analytically continue them into the full complex plane, and then look at the properties of the scattering amplitudes there. So I should say that unitarity implies an additional constraint. Actually, let me say this first. Okay, so we made this assumption here. You can ask how realistic it is. In fact, we know that unitary relativistic field theories are polynomially bounded. Which means that S of omega grows at most with some power of omega as omega becomes large. All right, and in fact, this notion in of itself has to do with the locality of the underlying theory. All right, so just to say one more thing about the signal model. So we can find further bounds on the signal model by imposing unitarity. So here, if we define the norm of our signal in the usual way, psi of t squared, then what unitarity means is that the norm of the out signal must always be less than or equal to the norm of the in signal. And you can show that, not surprisingly, what that means is that the norm of S always has to be less than or equal to 1. All right. So in the signal model, we get additional constraints in this way. All right. So now, in the 1950s and 1960s, people were able to prove rigorous theorems. Oh, yeah, sorry.
Sorry, so this analytic in the upper plane, that's only if you also assume that it is analytic in the sense that there's no branch cuts, right? For example, right?
Yeah, so
omega, you might still get the integral is 0, but it's not analytic just because you can't use the residue theorem, right?
So good. So you can show that these two things are necessary and sufficient for this causality condition being satisfied. So you're allowed to have poles and branch cuts precisely along the real axis. And in fact, people often use this I epsilon prescription to push these guys right below the real axis. But this is saying that you have no poles and no branch cuts in the upper half plane is a necessary and sufficient condition for S of t to be equal to 0.
So you can, so it's probably just a complex equation theorem. Or you cannot have branch cuts that are sitting in the upper plane, but still the integral is 0?
That's correct.
Okay.
And sorry, just to clarify, the unitarity constraint you're using is that you have positive norm.
So it's that the out signal should be, the norm of the out signal should be less than the norm of the in signal.
But what are you imposing at the level of the integral?
Oh, I'm just defining the norm to be the normal L2 norm of the field here.
Sure, you're using that. That's positive, right?
Yeah, it is positive, yeah.
Right. I was just asking in the context of negative non-states.
I see.
This not a positive one.
Yeah.
All right. Okay, very good. So in the 1950s and 60s, what people were able to do was to prove rigorous theorems relating the microcausality of the underlying quantum field theory to the analyticity of scattering amplitudes. So the analyticity of the S matrix in particular. All right. So why is this useful? What does this mean for constraining our physical theories? All right, so the typical object that's usually considered is a 2-to-2 scattering amplitude. Which we call A of S and T, and I'll unpack this. So in particular, we're going to be considering the 2-to-2 scattering of identical relativistic massive particles. So the process looks something like this. We have two particles coming in, which we label with 4 momentum P1 and P2. And we have two particles coming out with 4 momentum P3 and P4. And then we remain totally agnostic about what happens in between. All right, it's useful to talk about these problems in terms of Mandelstam invariance. So let me just define these very quickly. So S is the center of mass energy. It's given by P1 plus P2 squared. And this is equal to 4m squared plus k squared, where m is the mass of our identical particles and k is the momentum in the center of mass frame. We have T is equal to minus P1 minus P3 squared. This is equal to 2k squared cosine theta minus 1. Theta is the scattering angle. And we also have U equal to minus P1 or minus P4 squared, which is not really an independent variable, but can be expressed in terms of S and T, at least in 4 space-time dimensions, like so. All right, and so what we like to do is use these invariants, S and T, to categorize our amplitude, but you should think of these as being equivalent to just using the momentum and the scattering angle theta. So that's what we're encoding in S and T here. All right, the S matrix is this quantity S hat. And conventionally, we peel off the identity for no scattering and write this in terms of 1 plus some matrix IT. So that sandwiched in between our final and initial states, we can write T in terms of this AST, 2 pi to the 4. And then we stick in a delta function to peel out the conservation of energy and momenta, minus P3 minus P4. And it's this quantity A here. That's our 2 to 2 scattering amplitude. All right, and the conditions that we want to impose are the following. We're going to impose that our scattering amplitude is analytic, meaning that the only poles and branch cuts are going to appear along the real line and going to correspond to physical processes. We're going to impose polynomial boundedness. We're going to impose unitarity, Lorentz invariance, and crossing symmetry. So you can think of crossing symmetry as being related to the fact that if I flip the arrows on these two outgoing particles, this amplitude is basically completely symmetric under the interchange of these particles. And I can use that to relate the various Mandelstam variables. Yeah?
Does this polynomially bounded requirement break down as the number of scattering particles increases? Like an end-to-end scattering amplitude can be bounded by the same polynomial that a 1-to-1 or 2-to-2?
No, polynomials should hold independent of the number of particles. It's not specific for 2-to-2 scattering.
So I think in condensed matter, we would typically talk like the many-body density of states should ultimately become exponential.
I see.
Like your Hilbert space is 2 to the n versus qubits where n is scaled like volume. So
I mean, my understanding is that this follows from like axiomatic field theory. That basically it has to do with your Whiteman functions having sort of a local support, a local base, and from that you can conclude that your amplitude has to be polynomially bounded. But maybe someone who's an expert knows more.
He's just saying that the polynomial level, right? The n grows with the number of particles.
Oh, that's certainly true. Yeah. That's right. Sorry, that's absolutely correct. Yeah.
But for you, it's also important that if it grows exponentially, then analyticity would be broken as well. I mean, because it was important for analyticity that S atomic and not growing exponentially.
Yeah, that's right. That's right. Yeah. Okay. All right, so as a particular application of this, I'm going to consider an example that sort of led to the revitalization of people being interested in these types of constraints on effective field theories from 2006. So this is Adams, Arkani-Hamed, Dubovsky, Nicolas, and Ratazzi. And so what they did was consider 2-to-2 scattering in the forward limit. So that means t going to 0, or equivalently the scattering angle going to 0. In this forward limit, you can invoke the Faussart bound. Which states that this degree of polynomial boundedness we can actually constrict to be 2. So this means n equals 2. So this is for massive particles. This means massive particles. And in this case, the 2 to 2 scattering amplitude of these 4 identical massive particles, you're going to have poles located at s equals m squared. So now I'm going to consider analyticity in the s plane. So you're going to have a pole corresponding to s equals m squared. This is when your internal line goes on shell, as well as equal to 3 m squared. This is just the same pole, but coming from the U channel, as well as branch cuts. So there's going to be a right-going branch cut that starts at 4m squared, and another one starting, a left-going branch cut starting at 0. All right, so if I draw this, it's going to look like the following. All right, so this is S, and I have a pole here, and a pole here, and a branch cut starting here, and a branch cut starting over here as well. All right, and what the authors of this paper did is they said, let's consider the following contour integral. So consider an integral I equal to ds over 2 pi I, a sub s over s minus m squared cubed, where this contour here is meant to encircle the poles at little m squared, 3m squared, and this new scale capital M squared. So something that looks like this. If I put big M squared, say here, it's going to encircle these guys here. All right, so this integral I should be able to write just as the sum of the residue of these poles. And I should say this power of 3 here guarantees that A of S dies off as I need it to, given this Flessard bound here. All right, but note, because I know that my amplitude is otherwise analytic, the integral that I get from encircling these poles should be the same as the integral that I get by encircling these branch cuts and then closing the contour integral, the contour at infinity, like so. All right, so this should also be equal to 1 over 2 pi I, integral from minus infinity to 0, plus integral from 4m squared to infinity ds times the discontinuity, of the discontinuity A of s over s minus m squared cubed, like so. All right, but in fact, you can use crossing symmetry to show that the discontinuity is equal to, the discontinuity in A of s is equal to 2i times the imaginary part of A of s, so this is from crossing symmetry. But we know by the optical theorem that the imaginary part of the amplitude in the forward limit is directly related to the cross-section, so I can also write this as 2i s times sigma of s. So this is the optical theorem. And then crucially, we know that the cross-section is always strictly positive. All right, so what that tells us is that actually the sum over the residues in the low energy part of my theory, I know has to be positive. Yeah.
It's worth pointing out that so what you've written is the right optical theorem in the massless case, but it's worth pointing out that the optical theorem gets a little bit of a correction in the massive case.
Yeah, sorry. So there's like a square root factor here.
Square root, yeah.
And but this is always also strictly positive. But yeah, thank you for pointing that out. Yeah, I'm being a little hand wavy here. Yeah.
You also use analyticity in the bottom half?
Yeah, that's right.
did I miss? Do we know that there's a constant bonus?
Yeah. So the analyticity assumptions that we're allowed to make is that that all of the basically, and because you can think of this as saying that all of the non-analyticities are coming from actual physics, which means that they have to lie along the real axis. Yeah. All right. So this is something remarkable in the sense that, on the one hand, you're making assumptions about the UV behavior of your theory. You're saying, I don't know what the microscopic physics is of my theory necessarily, but I am going to assume that whatever it is, it obeys these following properties. And because of that, I can say something about the behavior of my low energy theory. So in particular, these residues are things that you can calculate completely just with knowledge of the low energy behavior of your theory, like so. So in some sense, even though you're remaining agnostic about what the IR physics is, you can use it to put constraints on the low energy physics of your theory. So the explicit example of this that was also invoked in this paper is you can consider a Lagrangian where you have a scalar field, massless with the usual kinetic term. And you add to it some higher derivative coupling, so some C over lambda to the 4, some d phi 4. And what these constraints would tell you is that C has to be strictly positive. All right, and what's nice is that you can directly relate this constraint back to a notion of causality. So in this case, you can suppose that your field phi has some expectation value or some value that you're expanding around. So I can write it as some phi bar plus delta phi, such that I can write d mu of phi bar as some vector field C mu. In which case, the dispersion relation for my field has to obey k mu is equal to minus 4c over lambda to the 4 c dot k squared. All right, now c dot k squared is something that's always positive. Lambda to the 4th is positive. And what you can read off from this relation is that, so this starts out as a massless field, so it propagates at the speed of light. The way that this correction is going to push the dispersion relation is that you're going to get something subluminal if C is positive, and you're going to get something superluminal if C is negative. So in other words, just by looking at the propagation of this field around some background, you would also conclude that C has to be greater than 0 to get good causal behavior of the theory. So this is a very nice relationship between what's going on in terms of causality between the amplitudes and what you might predict from the low energy theory to begin with. I should say, I don't know of many other examples where this works that cleanly, but it's nice that it works in this example. All right, you can generalize these. So more generally, you have the following statement. So here, S bar is a point on the real axis between the branch cuts. And this is the statement of the positivity of all even S derivatives of the pole subtracted amplitude. So in fact, you get an infinite set of positivity bounds on the coefficient of your low energy effective field theory. All right, so this is just one example. And like I said, this is sort of the example that revitalized interest in this type of program in recent years. There's been a lot of progress, a lot of work on this since then. Yeah?
I don't know, just final comments that this is what he used from the paper by Farm and Long, who use this stuff for pi scattering.
Yeah. So pi was the original example that thank you, that doesn't get enough credit. Yeah.
Just this kind of 40 years.
Yeah, thank you. No, very good. All right, so just a few notes on how people have extended this. So you can extend these types of bounds away from the forward limit. You can do arbitrary massive spins. Recent development includes this EFT hedron. Which derives a set of nonlinear positivity bounds, so they're bounds on products of coefficients. And these types of arguments have been applied to everything from pions to vector bosons to the Standard Model itself, to high-spin massive particles, and to theories of gravity also. So it has very wide-ranging applications, these types of constraints. All right. I want to switch gears a little bit and then talk about a different type of causality constraint that you can also impose. So like I said, in some sense, there isn't a single program imposing consistency conditions to constrain theories. So I want to talk about an alternative causality constraint, or I should say maybe a complementary causality constraint. All right, so this constraint also is focused on 2-to-2 scattering. But now instead of strictly being in the forward limit, I'm going to take the large S small t limit. So this is large center of mass energy, but also large impact parameter as well. And this is known as the Eikonal limit. And the nice thing about the Eikonal limit, from a scattering point of view, is that while in principle your amplitude depends on calculating an infinite number of diagrams, so the contributions to the amplitude in this limit all take the form of ladder and cross-ladder diagrams. So these are my ladder diagrams, and I also get cross ladders like so. This infinite, so these are the diagrams that contribute to this amplitude at leading order in this limit. And the virtue is that you can actually resum this infinite set of diagrams into a simple exponential of a tree-level Feynman diagram like so. And moreover, this tree-level Feynman diagram actually factorizes so that the only thing that you care about at the end of the day in computing this amplitude is the on-shell cubic vertices. So in other words, it only cares not only about the cubic couplings in your theory, but about the on-shell cubic couplings. And what's significant about that is that on-shell cubic vertices are actually incredibly constrained by Lorentz invariance. So that given any set of 3 particles, there's always only a finite number of structures that you can write down that's consistent. So these are always a finite number. So what that means is that you can test theories in an incredibly model-independent way. So you can say, okay, this is the particle content of my theory. I'm not going to assume anything about my Lagrangian. I can write down every possible on-shell cubic vertex for this theory, and then use that to calculate this scattering amplitude here in this regime. All right, so it turns out that if you calculate the scattering amplitude in this Eikonal limit, it goes like this. So B is our impact parameter. So e to the I, q is the momentum transverse to the impact parameter b, e to the I delta b minus 1, like so, where delta b is what's known as the Eikonal phase. All right, and what's useful about the Eikonal phase is that you can directly relate it to the time delay or time advance that a particle experiences in the scattering process. So I can write delta u, and I'll explain what this means, is proportional to 1 over pu times this delta b. So in other words, the idea is, so this is time, and this is my spatial coordinate. Suppose I'm scattering 2 light particles. So I have one particle moving like so, and let's say this is the v direction, my light cone coordinate, and another particle moving like so, and let's say this is the u coordinate. This particle is going to get deflected due to its interaction with this particle here, and in particular, I might expect it to show up at infinity, displaced by some delta u compared to where it would have shown up initially. And the statement that this delta u is greater than 0 is the statement that there's no asymptotic superluminality in your theory. So this is enforcing that your particle, due to its interaction, is always going to arrive more slowly than it would have initially. So this is the absence of asymptotic. All right, so if you have some theory, and in particular, you could imagine taking some healthy theory and adding to it, say, some higher derivative corrections. You can then calculate the 2-to-2 scattering amplitude in this Eikonal limit, and you can check explicitly whether or not this is obeyed by your theory. And in that way, you can put constraints on low energy theories. Oh, yeah.
So which class of theories does the amplitude equalize?
Good. So it doesn't work for low spin particles. I think it's known that for like spin 0 and spin 1, the Eikonal limit, you don't just get the ladder diagrams in that regime. But for spin 2 and higher, you can do this.
So say that in any theory for which you don't have scalar terms, so what's the statement?
So I think the statement is that if you try and take the Eikonal limit for a scalar particle, there are other diagrams that also contribute in addition to the ladder diagrams. So people haven't successfully applied these constraints to like scalar or vector particles for these reasons.
For any scattering of spinning particles?
For any scattering of scalar particles?
Spinning particles, you say this would apply?
So my understanding was that for spin 2 and higher it worked, but maybe there's some caveats in that. Yeah.
What do you exactly mean? Well, it's higher than no theories.
Good. Yeah. Well, good. So okay, good. I'll talk about what this is being used for. But I do mean higher spin in the sense that you can try and bootstrap up string theory this way, in which case you do expect to have a tower of high spin massive particles, and you can use the Eikonal limit for calculating amplitudes for those.
Theory you could just calculate, and sometimes it agrees with some kind of Eikonalization. Theory. For gauge theories, there are other problems.
You're saying for gauge theories you don't expect this to work, or for?
Well, we know what happens in gauge theory. It's more complicated. But we don't, in fact, know how this guy, how QCD behaves. Reggie argues.
I see. Yes, that's certainly true. Yeah.
Yeah, one quick just make sure that I said, even for spin 2 or higher external flex, the exchange particle can be the spin less than 2, or no?
No, sorry. It's the exchange particle that has to be the higher spin particle.
Oh.
Yeah.
Thanks.
Rachel, we have 2 more minutes?
3 more. Okay, very good. Okay. All right. So what I wanted to talk about was how do these constraints interact with gravity? And I'll go back to a specific example of this in hopefully the next 5 minutes. right, so there are two ways that you could interpret this question. You could try and determine constraints on gravitational theories. So in other words, treat gravity as the theory of a massless spin-2 particle and see what you can learn about potential UV completions of gravity in this way. The second question that you can ask is, how are these constraints modified away from flat space-time? So everything that we've been assuming so far assumes Lorentz invariance. We'd like to be able to think about constraints, for example, applied in cosmological settings or beyond. And so you might wonder, can you impose any analogy of these constraints away from flat space-time? All right, so maybe since I only have a couple minutes left, I'll talk about the application of this type of constraint to gravitational theory.
Rachel, could you just comment whether this also falls for massive spinning particles as well?
Yeah. So in fact, we did this for massive spin-2 particles and constrained the 2-parameter space. You get constrained down to a line from the 2-parameter space if you do it for massive spin-2s. Yeah. All right. Let's see. Okay, good. So maybe just to give a very brief background. So general relativity is a theory of particle physics. In fact, it's the unique low-energy effective field theory of a Lorentz invariant interacting massless spin-2 particle. Nevertheless, it's famously incomplete. It breaks down at the Planck scale, which is of order 10 to the 19 GeV. And so you might want to know, what is the correct theory of gravity at scales above the Planck scale? And so obviously this isn't a question that's necessarily completely answerable using these types of constraints. But what you might want to ask is things like, can you bound the coefficient of higher derivative operators in these theories? Can you determine the uniqueness of string theory as a perturbative UV completion? I think there are more ambitious questions that you could ask as well that are outside the bounds of the current constraints as we know them, but it would be nice to see if we could sort of improve our understanding of these constraints to tackle questions like, are there any consistent non-perturbative UV completions of gravity, or to how to calculate the gravitational S matrix in the ultra-Planckian regime. And maybe actually, since I only had 5 minutes, I won't go through the rest of the calculation, but I'm happy to talk more if people are interested. Thank you.
More questions? Steve, someone has asked a question. Well, just maybe.
I think you know more about this stuff than I do.
Well, there are a lot of mysteries, but one of the comments about gravity is you don't have a nice axiomatic starting point in terms of commuting local observables. So, you know, when you begin, you have to do something different.
Yeah, that's so. Are you talking in particular about like non-polynomial boundedness, or are you talking about something else?
Well, just for example, you started with the micro-causality statement, but the gauge invariant observables in gravity are not local, so you don't have the same statement to start with. Nonetheless, you know, it does look like there are arguments for, say, polynomial boundedness, but anyway, it's all inside.
Thank you.
Formally in quantum field theory, we impose micro-causality not on observables, but on the basic fields from sometimes observables and constructed. And we do have that in gravity as well.
You don't have gauge invariant statements like that.
Right, but you don't. You have, that's what ensures, as you know very well, in perturbative gravity, the analyticity properties of finite, which is all she was talking about.
Well, we want to go beyond perturbative, and even Eikonal is non-perturbative.
Of course you have to.
So I just think I didn't fully understand the statement A of S comma T only depends on on-shell cubic vertices. Is that a conjecture about exchanging of the above spin to particles. I don't think I understood what is the context of that statement, because apparently it doesn't hold if you exchange scalar particles.
No. So sorry. So my understanding is the following, that if you're considering low spin particles like scalars or vectors, then in this Eikonal limit, there are going to be other diagrams that contribute to this sum that aren't just the ladder diagram. So you could get things that look like, something like this, or more so, that are also going to be relevant. And then in that case, if you have these types of diagrams too, this sum is not going to be able to resum into a simple exponential like this. In fact, I'm not sure we even know how to resum in this case. And so for lower spin particles, you can't just say, in the forward limit, my amplitude is going to look like an exponent of a tree-level diagram.
So the statement is, if it resums to this exponent, then we only depend on, etc.
That's right. That's right. Then you can show it factorizes, and then you only need these on-shell cubic vertices.
Thank you.
Okay. Thank you, Rachel.